Welcome to the second session of the regression analysis program. Here we are going to pick up another example from an interview questions. These categories of questions are really important because sometimes the number of data or the number of samples might be small, but the interviewer go on and make it much more complex for the person who is sitting in front of the system. So regression models are a broad category of analysis. Here you can go for multiple contexts depending on the kinds of industry you are dealing with. You will get those kinds of data or the hypothetical explanation of the explanatory variables, right? So what we see is that we have been given a question here, that is how the relationship between training and sleep of a labor affect marginal product levels, right? That means we need to find a relationship which shows some degree of dependencies from the training and sleep part to the labor marginal productivity. Means we have our y variable as marginal product. Just by looking at the question, we have to sense this. Then it has also given a background that how we can go about it is that use regression analysis. The data is collected from 10 subjects. Therefore, find the levels of differences in marginal product that may or may not get affected by the explanatory variables. All right, if we just now go and see our data here. All right. So this is the kind of data that we are provided with here. We have total 10 subjects. We have their marginal product given. We also have data on their hours of training, that how many hours of training they have taken, and their hours of sleep is provided another column. All right. In regression, we have a dependent variable. So in our case, which is the, let's say, the marginal product or the efficiency, you also can say marginal product or the efficiency, right? So this y variable depends upon certain right hand side independent variables. That means we have a constant here. See this alpha value. What is actually showing that if the subject neither gets an hours of sleep nor it gets an hour of training, how that will be affected on the model, or how that is going to be affected on the efficiency or the marginal product that he has. All right. So quite instrumental for a constant value. All right. So it's completely separated from the variables that we're going to use. Right. We also can take the constant as 0, but given the fact that a person who is not even training and also if not sleeping, they're going to have some sort of impact. All right. So if you see the I'll just remove this part from here. We'll just calculate them one by one. All right. So if you see that the beta 1 here, the beta 1 value, what it's actually telling us that this is the coefficient of the hours of training, the x1 variable that we have here. That means this is going to show us a degree of impact to the hours of training that we have. All right. And same goes for the beta 2. That as we add beta 1 and beta 2, these two variables, the coefficient is going to show us the degree of dependencies that we have to the response variable. So this is also called the response variable, that will response given what happens with these values here. So hours of training, beta 1 and beta 2 hours of sleep. Also, we have taken an error term. If you can just see here, the error term tells us that we have just assumed that we have two variables here. So there might be some other superstitious power that the subject has. Even if they don't get sleep, they don't train, they might still perform good in the marginal product or the efficiency. So how do we actually go about that? This depends that what kind of or what sort of theories you assume. For example, we assumed something for the constant, and here also we're saying that we're not using all other variables. We only have two variables here, and the other things also might impact the model. So that's why we use the error term. Now what I suggest that you format your table the way we have formatted here. So for example, if you have hours of training as a first variable and hours of sleep as a second variable, so you put them into the reverse order, because Linus function is going to give you the x1 variable in the reverse order, and then the constant also, right? Here we're going to use the Linus function. So just type equal, right, LINEST, open the argument here, then select the dependent variable that we have, which is the marginal product in our case, then put a comma, then select the independent variables that we have, all the x1 and x2 variables, hours of training and hours of sleep. Then again put a comma, then it's going to ask you for the constant, one for the constant. If we want the constant values to appear, we put a comma, and also if you put one again it will give you the additional statistics. That means you're going to need the R squares, F stats, and so on, standard errors, to go for further analysis of the data. Okay, so if you just now close the argument here and if you hit enter, see we have a bunch of values appeared here. Now if you see, the constant value has given us a significantly negative number. What does that mean? That given the fact that if the person doesn't train at all and doesn't sleep at all, it's gonna impact his marginal product in a much more negative way. So the efficiency might even go to negative, because the marginal productivity is gonna go to negative. Now if we could have taken the alpha value as 0, we would have missed it. Maybe we would say that, okay, even if the person doesn't train or doesn't sleep, he will get some positive value in the marginal product, but that's not the case. It might reverse given the set of data that we have here. So for this example, again, the sort of assumption you made about your model is important. And then the x1, the hours of training variable we have here. See, if you can concentrate on the first coefficient value of the x1, it is 8.403615. That means every hour you train, your marginal productivity is expected to rise by 8.40 by this amount of number, which is out of 100. If you have a certain grade, and then if you train for 1 more hour, you will this will be affected by or increased by 8.403615 number. Alright, and also for the coefficient of x2, hours of sleep, this will also positively improve your marginal product. That means our model says that we have a positive relationship here. That means the more you train and the more you get you take sleep or you go for restings, your marginal product or the efficiency level is likely to rise. Right? This is what we are getting from this table here, for this Linus template here. Now can we say that this decision is reliable or not? Now this might be economically significant, but it has to be statistically significant as well, that how much reliable our data is. So if you can see the R square value here, it is 0.91%. So almost 91% of the variability in our data is explained by the two variables that we have here. Now is it significant to the result? For that we need to calculate the t-stat. So here for the t-statistics, you will just put equal, you will take the corresponding coefficient, you will divide it by the standard error of the corresponding column, which is in our case x2 here. If you hit enter, you drag them across. So we have our t-stat for all two variables and this constant here as well. Now how do we really go about explaining the t-statistics here? See, we have a much positive number which shows that it's likely to be statistically significant, to show reliable measurement for the model that we have here. Also for the hours of sleep, we also have a very good positive number, and we have a negative number for the constant. So how we explain the constant? That if you do not take any hours of sleep or external hours of training, if you do not do anything at all, then there will be a negative impact. So you're getting a negative value here. Okay. Now for the p-value, how we can say that it's not due to random setups of our data, but it's actually significantly effective to the model that we are bringing. We need to go for further p-values, so that we can much more reliably say, or with much more confidence we can say that, okay, these results have a good amount of impact on the variations that we have explained with the variable 1 and variable 2. All right. Now to calculate the p-value, we need two-tailed t-test here. So put equal t dot tist dot 2t, open the argument here, and then select the absolute value. Select the absolute value here, absolute value of the t-stat. Now it's a two-tailed t-stat, so we don't care about the number here. And then you a comma, and then we select the degrees of freedom here, and we want to lock the column as we are going to drag them across. Right now, if you close the argument here, do we hit enter? So we have our t-statistics arrived. So all the p-values and the t-stat values are giving us a significantly reliable number. So the three of this is below 1%, this is also under 5%, and this is under 10%. So this shows that the model with quite good confidence explains the overall data that we have here for the hours of sleep category and the hours of training category. All right. Now how we're going to say that the coefficients of x1 and x2 individually or jointly put in this effect. So to explain that, we want to go for a f-stat, where we want to see the effectiveness of all the coefficients that we have in our model. So for the F statistics, we have to divide the first R square here, the R square value we have divided by the number of regresses that we use. Here we have two regresses, which is x1 and x2. So 2, right? And then we again divide them. Start with a bracket here, and then close the first argument. Then divide it by the remaining variability that we have, which is 1 minus the same R square. It's going to be around 8 to 9%. All right. Then close the argument here. Then put a comma. Then we want the degrees of. We want to divide it by the degrees of freedom that we have, which is 7. So we have total 10 columns or 10 subjects. Sorry. Among them, we have used 3 categories here. So we are left with 7 degrees of freedom. We have lost 3. We have 7 degrees of freedom left. So that's we're gonna divide it by the degrees of freedom. Close the argument here properly, and just hit enter. So this one. All right. See, we have 39.3811, similar number that we have in this cell. So it's always better that you recheck the values that is provided by the line steplet, right? And for the p value as well. So that means the x2 and x1 jointly also gives us a much higher F statistics number. So the jointly improves the model that we have. Also, to check for the significance of the joint explanatory power, we also want to find the p value here. Type equal here, then write f dot dist. You want the f dist rt function in the argument here. This is for the p value, traditional method to find the p value. Now we want to select the f stat value that we have, right? If you put a comma, then how many variables that we have used to explain the dependencies that we have here. It is number 2. And then put a comma once again, and we have degrees of freedom 7, right? Then close the argument here. So we have degrees of freedom, we have 2 explanatory variables that we have used, and the value of the F statistics. Hit enter. See, now this I give you a percentage. See, this is 0.02. The p value has gone much down. That means jointly the hours of sleep and the hours of training explain the improvement of the dependent variable, which is the efficiency, and the relationship is much more positive, and it shows a reliable significance from the data, right? Also, now to double check the standard error, the explained sum square values, the residual sum square values, and the numbers that we have been provided in the R square portion as well. So what are all these values and how we can actually go and calculate and recheck them from our data here? So to manually predict the efficiency level, what we can do is that we just can reverse engineer our main equation that we have here, the way Excel understands, so that we can predict the efficiency level if the coefficients are not taken into account, right? How much the improvement may be brought by the first person and the second person, and so on. Okay. If we want to calculate the standard error, the explained sum square and the residual R squares, we need the predicted efficiency to actually find out the residuals. So with the help of these 2 columns here, we're going to find all these variables here, and we'll double check with the template that we have here, right? Okay. So to find the predicted efficiency, we'll just translate this to the Excel language. To do it, start that by writing equal, and then select the value of the first alpha, which is the constant. Okay, we'll just log the column for the alpha with plus. Then we select our first x1 variable that we have, the hours of training, this one. We log the cell that we have here, as we might drag them as well. Then we multiply them with the number of training hour that the first person have, right? This one. So we'll multiply it with this. Then let's say we again put a plus sign. Then we'll select the hours of sleep. That means the second variable that we have from the x2 category. All right. Select the coefficient. Again, just put a dollar sign here and block the cell. Then we'll multiply this with the x2 hours of sleep that we have in our data. All right. So this way we'll just see the predicted differences that we might bring, incorporating the coefficients that we have, that if we allow the influences to the model, that how the number will generate. All right. We just hit enter now. See, this is the number given to us. Just double click here and see we have all the predicted values that we can generate from translating the equation that we have. Okay. Now we also want to see the difference, that how much our model deviating from the real world. That means we are looking for the residual errors. All right. So here just put equal, just put equal and subtract the predicted efficiency level from the marginal product. Okay, and then if you hit enter, see the first value is minus 12, then minus 7. So there is a good number of influence we can observe from our data. All right, so by using these two values, the predicted efficiency or the expected outcome of our model, if we implement it, and then we have the residual errors. So what we feel that we might have some area of improvement into the residual error part. All right, so there is different values in different subjects cases, right? And that's a good thing. So the standard error says that how much on an average our model deviates. It will give us a number that if the real value is something like that, then how much our model can deviate, in a positive number, right? So the standard error is traditionally brought into a cell from the residual error from using these values here. Right, so what we're going to do, we're going to just write equal here, and we need the square root of the squared sum, the square root of the squared sum. Then if you correct, we need sum first here, the square root of the squared sum. If you open the argument here and you select all the residuals that we have, close the argument, and we have to divide it by the degrees of freedom that we have. All right, close the argument and just hit enter. See, we have 9.877. So our model might deviate in most of the cases by this number. If the real number is, let's say, 84, then just add 9.87 more values to it if you allow our model to go and implement. All right, so this is the deviation from the reality overall. Then we have the explained squared sum. It says that how much of the variability in the dependencies are explained by the two factors we have included. So we calculate them by putting equal here, and we use the variance dot population function here, the var.p, open the argument, then select all the predicted data that we have here. All right, and just multiply it by 10, that the number of subjects that we have. So it's 10. Hit enter. Here we have our explained squared sum number. Similar way, we can calculate the residual squared sum as well. So here also put equal var.p, open the argument, select all the residuals that you have, close the argument, and multiply it by 10. Here we have our residual squared sum as well. Okay. And finally, the r square is what is explained. So to calculate the r square, we put equal, and we say that the explained squared sum is this. All right, and what is left to explain, that means we divide it by the what is left to explain, that is the explained part plus the residuals part. All right, let's close the argument here, just hit enter. So see, these numbers are very much similar to the number that we have received on these columns. See, if you just zoom out a little bit, see, we have the 9.877621 as that number, standard error number, this one. Then the explained is this one. All right, and then we have the residuals part also matches with the r square that we have here. So I hope that you have understood that how we deal with the regression data that we are given in an interview. So you need to understand that explanations are much more important, and double checking your data manually is a must if you are taking up any task for the company or for the place you have been hired, right? So that's all there is for the Linus function and the multiple regression model. I hope you have enjoyed all the classes that we have organized, and in the January to June session, I hope most of the students will also attend upcoming workshops. Okay, so this is how we apply the data analysis method to the multiple regression model in Excel. Okay, so to deal with different kinds of data, I hope your theories helps you a lot, and in most of the outperforming cases, we see that interviewers are very likely put you into such conditions of data management. All right, so I'll see you in the next class. Thank you so much for joining. Have a good day.